Hello everyone, my name is Omri Aslach and today I present a joint work of Vadim Inzelman and I about experience-based prediction of unknown environments for enhanced belief space planning. In autonomous navigation in unknown environment, the agent starts from a point where it has no information about the environment. Simultaneous localization and mapping, SLAM, is the main approach to address this problem in the inference stage. Notice that the measurements are noisy and therefore the pose could be represented by Gaussian, and here you can see the uncertainty covariance of the last pose. Another task in autonomous navigation is decision making. The agent generates candidate actions and it needs to choose which action will lead to the best outcome. One method to deal with this problem is belief space planning. Using BSP, the agent performs belief propagation by a very similar process like it did in SLAM, but now the agent does the expectation calculation for future time. Next, considering the expectation, the agent calculates the defined objective function and chooses the action with the highest value of the objective function. In this example, the objective function is expected uncertainty, for example. But when the action leads to unknown environment, the BSP has some limitation and existing approaches currently perform belief propagation within unexplored area by only considering uncertainty due to motion model and without explicitly modeling the expected sensor observations because the map is missing. Related to the map prediction task is the impacting problem. In this case, we have an image with the missing part and the task is completed. Here, in the top right, you can see an example to how a human can do this mission. If a human can do it, so why not deep learning? So there is many works in this subject, most of them used variation autoencoder and GAN. We draw inspiration from the impacting problem for the development of map prediction algorithm that will aim to improve BSP in unknown environment. Okay, now let's try to understand the problem and the main contribution of this work. So current BSP methods lack the information necessary to predict future measurement in unknown environment. Therefore, in this work, we developed a map distribution prediction algorithm for the unexplored area for future measurement generation and the incorporation of this within BSP. In particular, we focus on planning tasks that consider the information theoreticals. This combination has not been done yet to the best of our knowledge. Now, we will dive into the formulation and start with SLAMI. I remind the notation here, X denotes the robot states or process, M denotes the map observed, Y denotes observations, and A is actions. Like we talked in the introduction, SLAM produced two outputs, the robot state posterior, the BK, we call that the robot state belief, and the map belief, MK. Both of them depend on history, that means the action and observation at current time. In BSP, we want to calculate the future belief that depend not only on history, but also on the candidate action and future observations. The objective function given by these equations, where the cost C is the function of the posterior future belief, which by itself depends on the future observation. So the expectation operator accounts for all possible realization of the future observations. To do so, we should be able to predict a future observation and approximate the expectation typically via sampling. The optimal action is the action with the minimum objective function. This diagram shows the problem that we are dealing with. you can see the inference stage and the planning stage. In order to generate observations, the map and the robot states are required. In our case, we focus on the situation where the goal is outside the map and therefore there is no access to the future measurements. Currently, these variables in the red color are uninformative. Also, we see the decision making depend on this measurement. So to address this problem, we would like to incorporate experience in the planning stage and actually adding experience for the map prediction. So here we show you the main development of equations. First, we incorporated available experience D within the objective function and rewrite the expectation as integration and sampled over Y distribution, the future observation. To sample future observation, YK plus 1, by observation model, we marginalize over the robot states, and the next submap MK plus 1. So for sampling future measurement, we sample over future map distribution. And here is where the purpose to leverage experience D. Now, our task is learn the future map distribution by experience-based prediction approach. First, in order to use the available current map belief from SLAMI, we marginalize over a capital MK. Second, because the map grows over time, we use only the submap with the constant dimension, lowercase mk. Note, our framework is general and we took the last simplifying assumption since the input in deep learning method usually is a constant dimension and that's more practice for the implementation. Now, we focus on the purpose to learn the future map, a distribution offline. The conditioning is the in this distribution is the submap and the action. For this purpose, we used a dataset of floor plans, transformed to occupancy grid, and finally we created our dataset that included sequences of the conditioning MA and the ground truth prediction M prime. In our work, we chose using conditional variation autoencoder architecture, which include two neural networks, encoder and decoder. In this case, the encoder maps from the conditioning and the ground truth map to the latent variable Z, and the decoder maps from Z and the conditioning map prediction. The loss involves two components. One is the error between the prediction to the ground truth, and second is this distribution at distance between the encoder output to the normal distribution that is sampled from in the deployment stage. So this is the training process, and when online in the deployment stage, we will use only the trained decoder. So we based on experience for the decision-making task, but incorporating experience doesn't necessarily improve results in all cases. And a question that you could ask is the experience relevant and relevant to the current task? So in order to detect some of these cases where experience isn't relevant, we suggested the novelty detection method. Novelty detection detects the cases where the conditioning is very different from the dataset examples and therefore may lead a wrong prediction. In our method, we measure the error in a copy operation of the overlap area between the conditional input and the map prediction. If there are construction error higher from defined threshold, the available experience is based on data that isn't similar enough to the current case. And therefore, a standard BSP method will be used instead. Now, we present the online process of BSP with experience-based prediction. The inputs are state belief, map belief, specific content detection, and trained decoder. The output is a computed objective function, which is approximation to the one I presented before. First, we convert the current map belief to the relevant submap around the robot. And next step, we will double loop. First look for n samples and look for L step action sequence. Next, we predict the samples of the next submaps using the train decoder. This is after one step, and here is merging of all the submaps around the candidate actions up time k plus n. Afterwards, we generate the future observation according to the map prediction sample. And in this example, the measurements is point cloud. Next, we update the belief propagation with the generate observation, and we calculate the cost function. In our case, we choose the cost to be the trace of the uncertainty of the last path. Finally, we calculate the objective function that averages the cost of all the samples over n samples. So in order to examine our approach, we compared it against existing BSP in a gazebo simulation, and the task is to choose the best action between the three action options. Here are the ground truth results of the three action options, and here you can see result of 5 samples for each action. The conditional map in light green and predicted map in dark green. Thus, there is much to be done to improve the results. The current performance shows that we predicted right the type of the future environments. As you can see, the corridor of action 1 and the room open source space for actions 2 and 3. We did a comparison between 3 methods of uncertainty evaluation on 3 different actions. Fifth, the optimal case when the robot using the ground truth of the future map. Our method, you can see when there is a different environment, there is a different uncertainty shape evaluation. In the black is the baseline method that considers only the motion model. And the comparison of all methods. We can see our approach in red predicts the uncertainty shape better than the baseline in black with respect to the ground truth. More results of this analysis. The figure in the left summarizes the cost function result of all the samples from the previous figures compared to the cost function calculated with the ground truth map method. And the red with circles represents the cost of each sample. The figure in the right shows objective function values for the 3 methods in contrast to baseline BSP. Our approach is the identical action order as the ground truth, like you see. Finally, we did the same comparison in 15 different cases and summarized it in this table. The table reports for each method the number of action ordering mistakes with respect to BSP with the ground truth map. Our method was preferable in 9 of the cases, against only 1 case when the baseline won. Also, we can see that our approach is improve uncertainty and cost error. Also, as you can see, scenario 15 is very different from the dataset. We calculated the reconstruction error for all the scenarios and showed that using the novelty detection method, we recognize unfamiliar environments and avoided using our approach in these cases. So in conclusion, we developed an algorithm that calculates a predicted distribution over unexplored area using a deep learning method, and we incorporated this distribution with BSP. We suggested novelty detection method for map prediction, and finally we compared our approach to existing BSP approaches in real gazebo simulation. The results indicate the potential to our approach to improve decision making in unknown environments. Thank you for listening.